This is podcast 2.6 for chemistry, and we're going to talk about the 4 periodic table trends. Atomic radius is the first one we're going to talk about, and that's the size of the atom. So the size of the atom, here's the actual definition. You can just think of it that way though. Trends within periods, remembering periods are rows. As we go across the rows, the atoms get smaller, and they do that because of increasing nuclear charge. Nuclear charge is the number of protons in the nucleus and the number of electrons on the outside. The more protons you add and the more electrons you add within the same energy level, you're going to create a stronger magnet, and it's going to pull that atom in tighter and closer together. So it actually gets smaller as you go across the row. Trends within groups, those are your columns. As you go down a column in the rows, we know that this would have a nucleus in 1 energy level. This has a nucleus in 2 energy levels. This has a nucleus in 3 energy levels. So you're going to get larger atomic radiuses as you move down because you're increasing the number of energy levels. They also will sometimes throw in the word shielding. It's a shielding effect. That's because these electrons that are way out here are starting to get shielded by all these inner electrons. So the nucleus has a hard time pulling those outer electrons closer to the nucleus. You get too much stuff in the way here. So if we looked at a picture that showed us some atomic radii, or the sizes of these atoms, we can see hydrogen's pretty tiny, and as we move down the column, we're seeing that they get bigger and bigger and bigger. But if we take this example right here, and you kind of need to disregard these, they follow the trend a little bit, but you just kind of want to pay attention to the first, second, like 1A, 2A, 3A, 4A, 5A, 6A. So if we do that, we can see that as we go across the row, they're getting smaller and smaller and smaller and smaller. That's because of the increased nuclear charge. And smaller and smaller and smaller and smaller. Now you are going to be able to find exceptions. There's just how it is. But in general, the trend we're looking at is that it gets bigger as it goes down and it gets smaller as it goes across. So let's flip over to that periodic table that you have that's blank, and we're going to add some arrows here. So as we go down like this, we said that it increases, it gets bigger. And then as we go across this way, it's going to decrease. So that tells me that francium down here should be the biggest. And helium way up here should be the smallest. And if you want to draw like a general trend, I don't know which way you prefer, the increasing or decreasing. You can draw a diagonal line like this that shows that it increases. Well, I should probably write it where you can see it. Increases that way. So increases going down, decreases going across. That's atomic radius. The next one is ionic radius. And ionic radius can be a little tricky because you have both the positive and the negative anions and cations. So the ion is the same as, the ionic radius is the same as atomic radius, it's just the size of the atom or group of atoms. Here's the really important part, is that when atoms lose electrons, when they lose those electrons, they become smaller. And when they gain electrons, they become larger. And that is because if you're losing, it's like if you lose anything, you get smaller. People who lose weight get smaller. When you're losing things, there are less electron-electron repulsions, so there's more room for the electrons, and everything can pull in tighter together than it was before. When you're adding more electrons than what it's used to, you get these more repulsions than what it was used to without the increased protons in the nucleus. So bigger means you're gaining electrons, smaller means you're losing electrons. Within a period then, as you go left to right, the size decreases. And then within a group, it's going to decrease as you, nope, this is the one that was the typo. Make sure you change that to increases. This is going to increase as you move down a group because you're getting more energy levels. So make sure you change that on your paper. Let's look at some pictures. So here's some examples. You can see what lithium looks like before and then after it's lost its electron. Sodium, and then after it's lost its electron. And you can see that when they lose more electrons, they become smaller. So a +1 compared to a +2 compared to a +3 is much, much tinier. Down here, the opposite is true. I have the nitrogen atom, and then after it's picked up the 3 electrons that it wants, it's much, much bigger. Oxygen picking up its 2, fluorine picking up its 1. And you can see that when it picks up more electrons, the bigger it gets. So then 3 negative is bigger than the 2 negative, which is bigger than the 1 negative. So let's go to our periodic table and let's draw some arrows in. We said that the easy one here is that when it goes down, just like atomic radius, it's going to increase. And then it gets a little tricky. So I'm going to draw kind of a divider line right here through carbon because carbon is weird. It can go both ways. So from here to here, it's going to decrease in size because we're going from +1, +2, +3. Over here, though, where it's -3, -2, -1, and I'm going to exclude the noble gases because they don't form ions in this, so we're not going to think about them. Get rid of them, get rid of them. Okay, so -3, -2, -1, these are also going to decrease this direction. But that being said, these negative ions are bigger. So the negatives are bigger. The positives over here are smaller. So the same general trend, they both decrease going left to right, but you just need to understand that these are bigger than these ions over here. And this would be the +1, +2, and +3. All right, next one is ionization energy. Here's the definition. It's really big and long. This is kind of the abbreviated one. It's the energy needed to remove a valence electron from an atom. And we're only talking about first ionization energy, so just removing 1 electron and that is it. Trends within periods, they're going to increase as you move across a period. So as we go across those rows, it's going to get more because of increased nuclear charge. So as the atom gets smaller, like we said, that's what happens when you go across. It gets a lot harder to pull those electrons away because they're being held a lot tighter because of the nucleus. Trends within groups, it's going to get easier to remove those electrons because of the size increasing. So this is opposite, this trend is opposite of atomic radius. And it really has the same reasons. If you think of going down a column, you have your nucleus here and an electron in the first. You have your nucleus here and then this valence electron. You have your nucleus and then this valence electron. It's going to be so much easier to pull this electron away because of all this other stuff that's in between it and the nucleus. So the bigger your atom gets, the easier it is for you to pull those electrons away from the atom. That's why it's opposite of atomic radius. All right, so here's a picture. It's kind of blurry, but you can see that as we go down the column, that ionization energy drops. It gets a lot easier, so it's easier to pull a potassium valence electron away than it is a sodium valence electron. And that's because size is becoming bigger as you go down, so there's more stuff in the way, so it's easier to pull those electrons off. And we can see that the trend as we go across, for the most part, there's always exceptions, is that it's increasing. The smaller it gets, the harder it is to pull those electrons off. So let's look at your periodic table and let's draw some arrows. So we said that going down, it actually decreases. It becomes easier to remove electrons down here. And going across, your ionization energy is going to increase. This is exactly opposite. Francium then is going to be, or it's going to have the smallest ionization energy, and helium up here is going to have the highest ionization energy. It's going to be the hardest to pull it away from helium. And if we want to draw our arrow this time, this is the increasing diagonal arrow that way. Okay, last one is electronegativity. Electronegativity is how much atoms attract electrons during bonding. So if you think of metals we know like to lose their valence electrons. So they are not going to want to attract anything during bonding. They want to lose, which means they're going to have lower electronegativities as opposed to your nonmetals, which we know have 5, 6, or 7 valence electrons. They're looking to gain those electrons during bonding. So they're going to have much higher electronegativities because these are the ones that want to pick up electrons, so they have high electronegativities. These guys want to lose their electrons, so they don't attract much during bonding at all. Trends within periods. So as you go across the row, it's increasing, and that's because of what we just talked about. The nonmetals on the right-hand side want to pick up electrons. The metals on the left want to lose electrons. And then trends within groups, it decreases as you move down a group because the nucleus is shielded. If you put a lot of stuff in between the nucleus and the outer valence electrons, it's a lot harder for that nucleus's positive protons to have a pull on any other electrons. So this also is opposite of radius, atomic radius. I guess I should put that in. Atomic radius. And it's the same as ionization energy. Here's a picture again where you can see actual values. These values do not have units. They are relative values compared to each other. So you can see that fluorine here is a 4.1. It has the highest electronegativity on the periodic table. The noble gases are not included because they don't bond, so they are zeros. And then over here you can see francium is down with the lowest. Cesium, barium, radium, they're all really, really low down here at 0.9. Even potassium. Your alkali metals in general do not want to attract, and you guys should understand that because they only have one valence electron. They don't want to gain any more, so their electronegativities are really, really small. Then to draw our arrows in, we said as you go down the row, it decreases, or as you go down the column, it decreases. As you go across the row, it increases. That means we're going to get rid of these because they don't bond. So again, fluorine is going to be the biggest in terms of electronegativity. Francium and everybody down here is the smallest. So if we want to draw our diagonal arrow again, it goes this direction for increasing. Make sure that you know the direction the trends go and that you also understand why they do those things, that you can give an explanation, not just because that's the way the trend goes. So make sure you understand the reasons why behind these trends.